All right, so let's get started with 9.6 counting principles. And so this section and 9.7 are going to introduce some basic counting principles, permutations, combinations, all right, things like that. And then we're going to use some probability in both these chapters, mostly in 9.7 though, all right, to figure out the probability. So in this section, 9.6, we're mostly going to figure out how many different ways you can count things, all right? And we'll have a couple formulas to figure out how to do that. So, example 1. 8 pieces of paper are numbered from 1 to 8 and placed in a box. One piece of paper is drawn from the box, its number is written down, and the piece of paper is replaced in the box. Then a second piece of paper is drawn from the box, and its number is written down. Finally, the two numbers are added together. How many different ways can a sum of 12 be obtained? All right, so if we make a little list here, we can try to figure this out. All right, so different ways we can add up to 12. And remember, we can only use 1 to 8. So we could use 4 plus 8. We could use 5 plus 7. We could use 6 plus 6, and that's allowed because we're putting the numbers back in. We're replacing them in there. All right? We could pull out a 7 and then a 5. That's different than a 5 and then a 7. The order matters. And we can pull out an 8 and then a 4. All right, so 5 different ways to do this. All right, so using the same kind of thinking, see if you can tell me how many different ways you can get an integer that is divisible by 4 from 1 through 12. This is, don't overthink this. This is very simple. Alrighty, so those 8 pieces of paper are numbered from 1 to 8 and placed in that box again. 2 pieces of paper are drawn from the box at the same time, and the numbers on the piece of paper are written down and totaled. How many different ways can a sum of 12 be obtained now? Okay, so now we know that it's going to be 4 plus 8, 5 plus 7, 7 plus 5. We're skipping the 6 plus 6 because we can't get a 6 and then a 6 because we're drawing the numbers at the same time. There's only one 6 in that box. And then 8 plus 4. So in this situation, there's only 4 ways we can add up to 12. All right? So in this case, the replacement changes the problem. So see if you can figure out this one, slightly different than 11, numbers 1 through 12. How many of those, if you added them up, you would get 9 if they were distinct. Can't repeat numbers is what that means. Distinct means can't repeat the numbers. All right, this brings us to the fundamental counting principle. The difference between the counting problems in 1 and 2 can be described as saying that the random selection in 1 occurs with replacement, whereas the random selection in 2 occurs without replacement, right? The 6s. All right, so examples 1 and 2 describe simple counting problems in which you can list each possible way that an event can occur. When it is possible, that is always the best way to solve a counting problem. However, some events can occur in so many different ways that it is not feasible to write out the entire list. And these are the problems we're going to deal with a lot. If we have 700 different ways something can happen, we're not going to write out all 700 ways. All right? We have to rely on some formulas and counting principles, starting with the fundamental counting principles. So let's look at this. E1 is some event that's going to happen. E2 is some other event. All right? If the first event can occur in M1 different ways, okay, and after E1 has occurred, E2 can occur in M2 different ways, the number of ways the two events can occur is M1 times M2. You just multiply them together. And you can extend this. If there's 3 events, M1 times M2 times M3. All right? Now the key here is E2 is happening after E1. Not simultaneous, but after. So we'll look at some of these. How many different pairs of letters from the English language are possible? So we're going to first pick one number. How many numbers are in the English alphabet? There's 26. That's going to be our M1. And then we just multiply how many numbers are in the alphabet again, because that would be our second option. We make those pairs. 26 times 26. I don't know how many that is off the top of my head. Let's go find that. Got all this regression stuff still in here. What's 26 squared? 676. So that would be our answer here. 676 different 2-letter combos from the English alphabet. All right, so your turn. In how many ways can a 6-question true-false exam be answered? Okay, can't skip problems. All right, using the fundamental counting principle again, we have 10 digits in our telephone numbers here in the U.S. First 3 are area codes, next 7 local telephone number. You guys know that. How many different telephone numbers are possible within each area code? At this time, a local telephone number cannot begin with a 0 or a 1. All right, so our first number, and I like to do this. I like to have placeholders for all my options. So there's my first 3, and then the next 7 of my phone number. All right, since we can't use a 0 or a 1, there's 8 options that could go there. And then there's 10 options that could go in each of the other spots, because these numbers could be 0 all the way up to 9. All right, so for simplicity's sake, that's 8 times, remember we're multiplying all these numbers here, 10 to the 6th. So that means 8 with 6 zeros, otherwise known as 8 million. All right, so that's how many different phone numbers we can have in the United States. 8 million different phone numbers. Okay, that's not enough. 8. How many zeros did I left out? 10 to the 8th. Sorry. No. 9. Man, can't add up tens, can I? 10 to the 9th. 8 million didn't seem like enough phone numbers for the whole U.S. 8 billion. 8 billion. Sorry about that. Count up all your zeros. There should be 9 of them. All right. See if you can do this better than I did the last one. A combination lock will open when the right choice of 3 numbers from 1 to 40 is selective. Inclusive means you can repeat numbers. How many different combos are possible? Okay, so permutations. First new thing we're going to introduce after the fundamental counting principle. All right. How many different ways can we arrange things? So order matters. All right. If order matters, we're going to do a permutation problem. A permutation of n different elements is an ordering of the elements such that one element is first, then is second, and then third, and so on. How many permutations are possible for the letters A, B, C, D, E, and F? Okay, so how many letters are there? There's 6. So I could pick 6 of them to go first. How many could I pick to go second? I could pick 5 because I already picked one. All right, the order matters. And then 4, and then 3, and then 2, and then 1. All right, so 6 times 5 times 4 times 3 times 2 times 1. You guys know what that is. That's 6 factorial. And what is that? 30 times 4 is 120. 360 times 2, 720 is the different permutation. So they get very big very quickly. Your turn, 39. How many different ways can we get 5 children posing for a photo lined up in a row? So order matters. Okay, so number of permutations, obviously you guys just saw that, is a factorial problem. So if we're doing permutations, we just do factorial. All right? So, but now what about if we don't want all of our options included in our answer? So in this example, we got 8 horses in a race. We only care about first, second, and third place. All right? How many different ways can the horses come in? All right. First place, how many horses are there that could finish in first? There are 8 of them. But once a horse wins, there's only 7 left for second place. And then there's 6 horses vying for third place, and at that point we're going to stop because we don't care about the rest of the losers, 4th through 8th place. So 8 times 7 times 6, that's our answer, and that is 336 different first, second, and third place winners. All right, see if you can answer 41 using the same thinking. Okay, so that brings us to a formula for permutations if we're not going to use everything. The number of permutations of n elements taken r at a time. 8 horses taken 3 at a time. Okay? n factorial over n minus r factorial. So we'll subtract and do the factorial on the bottom. All right? Now, what about if things repeats? For instance, I've got this list, A, B, C, and D. If I take 3 of them at a time, we could have some different permutations, right? But what if I had a double up of A's in my list, okay? I would have 4 options to choose from, and I would pick 4 of them. Okay, I don't know if I mentioned that here. This is how many, n is how many we have to choose from, r is how many we're actually picking. Okay, so we have 4 to choose from, and we're picking 4 of them. Okay, but A, B, D using this A is no different than A, B, D using this A. I'm sorry, A, B, C. They changed the letters on me, right? A, B, C versus this A, B, C are not different. They're not distinguishable, okay? So if we have a situation where we need to figure out the distinguishable permutations, we're going to do n factorial, okay? That's how many we have to pick from, divided by n1 factorial, n2 factorial. That's how many repeats that we have, okay? So let me show you an example here. How many distinguishable ways can we do banana? All right, so banana is going to be, there's 6 letters in that word, so 6 factorial. Divided by, are there any repeats? Yes, A repeats 3 times, so we're going to do 3 factorial on the bottom. And N repeats twice, so we'll do a 2 factorial on the bottom. Okay? So this is 6 times 5 times 4. Once we hit 3, those cancel out. Divided by, we still need 2 factorial, divided by 2 times 1. Okay? So 2 times 1 cancels out the 4, makes it a 2. 6 times 5 is 30, times 2 is 60. 60 different ways to write banana. There's all of them. Okay, so now you can see why we want to go ahead and use the permutation formulas instead of writing them all out. Don't do that. You're up. How many distinguishable ways can we group these letters? All right, so that brings us to combinations. Combinations, we don't care about the order. ABC and BAC are exactly the same. So we're going to use this in a lot of situations, but the key on this is when to use them is if order does not matter. Okay? All right, how many different ways can 3 letters chosen from this list? Okay? Remember, the order of the 3 is not important. Okay? So we could use ABC. We could use ABD. We could use ABE. All right, let's change up the middle letter. We could use ACD. We could use ACE. And then we could use ADE. All right, let's start with B. We could use BCD. We could use BCE. We could use BDE. And then lastly, we could use CDE. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways. All right? So go ahead and make yourself a list for 61. All right? All the possible selections of 2 letters that can be formed from A, B, C, D, E, and F. And the order is not important. We're doing combinations, not permutations. All right, so there's a formula for this, and it's going to be right here. Okay, so it is the number of things we're picking from, and then how many we're actually going to pick is n factorial over n minus r factorial. Exactly the same as permutations, but then also divided by r factorial. So you'll see here, it's the permutation formula divided by r factorial. Okay. All right, so standard poker hand consists of 5 cards dealt from a deck of 52, and if you've never seen a deck, I don't know how that's possible at this point, but there's all the cards. How many different poker hands are possible? After the cards are dealt, the player may reorder them, so order is not important. All right, so let's go back to our formula. We're picking from 52 5 different cards. So the formula is going to be, if we go back up, n factorial, so 52 factorial, over, do the subtraction, 52 minus 5 is 47 factorial, times r factorial, 5 factorial. So, in the numerator, 52, 51, 50, 49, 48, and I'm going to stop because then we'll cancel the 47s, over 5, 4, 3, 2, 1. And if you do a combination problem right, you should have the same number in the numerator as you do in the denominator, okay? All right, so let's see if I can cancel here. 4 times 3 is 12, times 2 is 24. So that'll go into 48 twice, and 5 goes into 50 10 times. Just want to make my numbers a little smaller before I put them into the calculator. So let's see what we got here. 52 times 51 times 10 times 49 times 2. And we've got 2,598,960 different combinations. Now, let me go ahead and show you how to do that with the calculator. We're going to hit Math, go over to Probability, and pull up our combination, NCR. And, oops, sorry. You have to hit 52 first. 52, and then NCR, number 3. So 52 is your N, and then you type in your R, which was 5. And we get the same number there. So that's how you can use calculator, and you can do the probability as well, same way. You're up. 63. From a group of 40, we're picking 12. All right, last example. We're forming a 12-member swim team, 5 girls, 15 boys. The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? Okay, so 2 different events here. Okay, we've got basically we have a girls team and a boys team, right? So we're going to pick 10 girls, and we're going to pick 5 of them. And we're going to pick from 15 boys, and we're going to choose 7 of them. Order doesn't matter, you just want to get on the team. And from the fundamental counting principle, if 2 different events happen, we're going to multiply them. First we're going to pick the girls, then we're going to pick the boys. So 10C5 is going to be 10 factorial over subtract them, second number, times 15 factorial over subtract 15 minus 7 is 8 over 7. 10, 9, 8, 7, 6 over 5, 4, 3, 2, 1 times 15. I'm going to go all the way down to 9. All the way over 7. And let's do some canceling. 3 times 2 is 6. 4 goes into 8 twice. 5 goes into 10 twice. So 9 times 7 times 4. $252 times 5 times 3 goes into 15. And let's see. 6 times 2 would get me to 12. And that seems to be everything that's easy so far. So, calculator. 14 times 13 times 11 times 10 times 9 divided by 28, 7 times 4 in the denominator. 6435, let's times it by 252. So there are 1,621,620 different ways. Let's do the NCR to make sure we did this right. So we had 10C5. 10C5, 252, and we had 15C7. 6435. Multiply them together and we get that same number. So, wrap this up. Try 71. Oh, we're spinning. I'm going to pause the video until it stops spinning. But wrap it up with 71 and you're all done. Alright, there you go. There's your last problem, 71. Oh, the smart ink is killing us here. Hold on. There we go. Solution coming your way. There it is. All right, just one last thing to consider here. All right, is the order important? Permutations. Is the order not important? Combination. And if you got two separate events, multiply them together. Fundamental counting principle. You're done with 9-6.